Okay, so this first section, we are talking about identifying linear functions. So you guys have some experience with functions. Like last year, we made those function machines where you have an input and an output. Well, this year, we are talking about specific functions, and these ones are linear. So with a linear function, and I know some of this vocab can be intimidating, but what you have to remember that a linear function is just a line, okay? And the word is right in the word linear, line. So it says linear functions can be represented in many forms. The same function is represented below in 5 different ways. So I'm going to represent this function as a graph, a set of ordered pairs, a table, like notice here, -1, 5, 0, 3, 1, 1, 2, -1. We could write this as an equation. Equations can look different. That's why this chapter focuses on so many different things. And then a sentence, the sum of 2 times x and y is 3. Okay, you guys won't see that verbal sentence very often, but you're gonna see the other things. You're gonna see tables, you're gonna see graphs, and you're gonna see equations a lot. So the question here is, how can you tell if a function is linear? So there's a few different ways, and we are going to break this down into basically graphs, tables, and equations. So in order for a function to be linear, it has to be 2 things. The first thing is that it has to pass the vertical line test. Okay, so the vertical line test is when we look at a graph. If we imagine drawing vertical straight up and down lines throughout this entire thing, it doesn't touch the same line twice. That's right. So right here, it only passes once, it only crosses once, crosses once. So this one is a function because it passes the vertical line test. Okay, well, let's do the next one. If you did the vertical line test, does it pass? Yeah, it only crosses the line once. What about the last one?
No. Wait.
Yes. Yep, it does.
Wait, so it has to like intersect the line once.
When you draw a vertical line, it can't cross twice. So my example that is not linear is right here.
Oh.
If your graph was curved, okay, if I drew this vertical line, it would cross here and here. That means it fails the vertical line test.
So like if this first example was like rotated 90 degrees, it wouldn't pass.
That's correct. Yes.
So they're all yes.
So all of these are functions, okay? So then we can say yes, yes, and yes. How do we explain it? Okay, well, it passes the vertical line test, and I'm just going to use an abbreviation, VLT, for that. And then we would say passes the vertical line test, and then yes, passes the vertical line test. It does sound like that. So then the next part, it says, if the graph does represent a function, so all of these are functions, is it linear? What do you think it has to be linear?
Straight.
A straight line. Is the first one linear?
No.
No, it is a V. So yes, it's 2 straight lines, but it's not linear. Okay, so yes, a function, but I'm going to say, but not linear.
How would it be a function?
Because it passes the vertical line test. So that's okay.
The second one is no.
But it's not linear. So is this one linear?
Yes.
Is it a straight line?
Yes. What?
It's just a
It's
straight
line. It's just not.
Yep, it doesn't have to be like straight vertical or straight horizontal. So this one is, yes, linear. And then what about the last one? Is that a straight line?
Yes. Yes. Full show.
Yes, linear.
Full show.
So in order for it to be a linear function, it has to pass the vertical line test and be straight.
In order to be a what?
A linear function.
So if it doesn't
So-
pass, then it's not.
Yes. So I'm just gonna write that up here. Has to pass the vertical line test and be a straight line. Now, I know some of you are better than others in filling out your notes. Just remember, the more info that you put down in here, the more resources you have.
I thought you were going to say the more credit you have. I was like, I don't know, right?
Okay, so that was the focus on the graphs. So the next stage that we're going to take it is how can we tell if we look at a table? And I'm going to scan back up to the beginning. Do you notice in this table that the change of the X values, they went up by 1 every time, and the change of the Y values went down by 2 every time. So here's the rule with a table. In order to be linear, I know it's kind of hard to write here, but there must be a constant change or constant difference. And so in this case, there was a constant change of -2 and then a constant change of +1. They didn't have to be the same change, but there was a constant change. So, well, I'm going to do more examples, okay? So then if we go down to our examples here, from 4 to 6 to 8, it went up by 2 every time. Do you see that?
What was the other one?
1 second. Yep, but this one went up by 1 the first time and 2 the second time. Is that constant?
No.
No, so if it's not constant, it's not linear.
So if the number changes? No.
That's right. If the number changes from, it's not constant. So I'm just going to circle this right here. And I'm going to say not a constant change. That means that it's not linear.
What the other one?
Well, this is all one function. Or are you talking to me this one?
No.
So this one had a change of 2 on the one side, which is good, but then it, oh, the one on the top did have a constant change. It went up by 1 every time and then down by 2. And so they can be different from each other, but they both have to be consistent on each side. So we'll look at the second example here. So from 2 to 5, how do we get from 2 to 5?
3.
Yep. And what about 5 to 8?
+3.
Yep. 8 to 11.
+3.
Good work. Okay, so then 4, yep, -1. That's right. So are these constant? Yes. So we can reply that yes, this is linear. And if you had to say why, you would say because there is a constant change, constant difference between the X values and the Y values. It's a big deal there. Constant change.
So it's a no if it's one side and then the other side.
Mm-hmm.
You get what
Yeah,
I'm
so the example on the left, by these ones not being constant, it blew the chances of it being linear.
What is can't
I can go back, sorry. Brad. Sure.
Every time someone says that, it makes me happy.
Okay, so the last type that we're gonna look at is from an equation. And the nice thing about the equation is basically there's just some rules. Now, they talk about standard form, and we'll maybe touch on this later on in this chapter, but standard form basically is when an equation, instead of being written like this, is expressed with the x and y both on this side and the number on the other. So they say in standard form, x and y have exponents of 1. So basically this means they don't have any exponents. So no exponents. There's an exponent in there, it's not going to be a straight line.
Where are you writing that?
I just wrote it right next to the box here. X and y are not multiplied together. So for example, you couldn't have 2 equals 3xy.
How do you write so small?
Practice.
You can't write that small?
Okay.
I hold my
If I do, it looks like squiggly lines.
So like having an exponent would be like y equals x to the 4th. That would mean that it is not linear.
Why? Did you time?
Because it ends up getting big really fast. It makes not a constant difference. Like I could even show you what that would look like.
There's no way it could be.
Yeah, because it changes so much every single time. So if you put a 1 in, you'd have 1 to the 4th would just be 1, right? But if you put a 2 in, this is your x, this is your y. If you put a 2 in, it'd be 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. If you put a 3 in, I want to say it's 81. Yeah. So, Maddie, do you see the differences here?
Yeah.
This one went up by 15, and then 81 minus 16, yeah, 81 minus 16 went up by 65. So do you see how not consistent that was? Even though these only went up by 1. Okay, good question. So, and then the other rules is that x and y cannot be in the denominator, they cannot be in an exponent, or they cannot be under radical sign. So just to give you guys some more visuals there, we cannot have x in the denominator, so you cannot have like y equals 4 divided by x. It can't be an exponent, so you couldn't have y equals 2 to the x. And these are just examples. These aren't the only ones. And then underneath a radical sign. So for example, you couldn't have y equals the square root of x. Any types of those equations will not produce a straight line.
How do you know?
Well, in my math career, I have graphed these different things. Okay, so I know what happens when I put in a value for x and 2 and that kind of thing. So I know that they will produce lines, but they won't be straight.
Dylan fell down.
Okay. So then if you guys just take a peek here, even without getting these in standard form, most of the time you can pick out the ones that fail. So I'm sure that you guys can look at A, B, C, and D. Can you pick out one that does not meet all of these rules, or one that doesn't pass these rules? Go ahead, Maddie.
So
Which one?
y equals.
Well, we're going to talk about that one last, okay? C, why C? Yes, x is an exponent, so this one's not linear.
When we talk in the box, with all the examples and stuff, they're not linear.
That's right, not linear.
So stuff that like having going to one, all that stuff that means that they're not linear.
Yeah, yep. Or, I mean, this kind of means like, yeah, these examples are not linear. So not linear because x is an exponent.
Where are you writing that?
Right there. Okay. What's another one that's not linear?
B.
B, right. Oh,
He said
yep.
B.
So this one's not linear. And it's not linear because x has an exponent. Because x has an exponent. B. Okay, so now we're with A and D. Now A, does it break any of the rules? Are there any exponents?
No.
Nope. Are X and Y multiplied together?
No.
No,
Wait, so we can't have an exponent at all?
it cannot have an exponent at all. Are X or Y in a denominator underneath a radical sign? Any of those things?
No.
No. So then this one is yes, linear.
Wait, so it can't have an exponent on X, but can it have an exponent of like a number, like 3?
X or Y cannot have an exponent. X and Y cannot be in an exponent.
Well, like,
So-
if it was this equation, and it was like y equals 3 to like the third power or something
Okay, so
plus x.
yes, that's a great question, Bethany. So can there be an exponent? Well, Bethany, can you technically simplify this exponent?
Yeah.
Yes. So if you can simplify this, then that's fine. The reason why X and Y cannot have an exponent is because there's inputs and outputs, and that will skew things.
It's
Okay.
27.
More than that.
It is?
It. Oh no, you're right. Yeah. Sorry. You're right. Okay. The last one, and this is a special case. If we had this on a graph, and I know that you guys haven't really seen this yet, we will talk about them to come. This is what this line would look like.
Draw a little tiny graph.
Okay, now this right here is y equals 12. Now, if what you know about linear graphs, does this pass a vertical line test?
No.
Yes.
It does. If you drew a bunch of vertical lines, it would pass. Is it a straight line?
No. Yes.
Yes, it
Yes.
is.
Oh my gosh.
Okay,
No, but
so listen to this. It is a straight line and it does pass the vertical line test. So this particular one is linear.
But
Now, this is a special case because I'm going to talk about, I know that you guys are like, well, where's the X? But there is, every X equals 12, or every Y equals 12, okay? So now here is the catch. Here's the alternative. X equals 12 would look like this. See if I can fit this in here. This is X equals 12. Is that a linear function? Does it pass a vertical line test?
no. No.
No, if I drew a vertical line, it would hit every single point on that line.
Over.
Yes, so Y equals 12 is linear, X equals 12 is not linear.
Don't you know if it goes like this way?
So we are gonna practice these more and you will learn about them in further units. This is just a little glimpse of them, okay? The way that I remember, Maddie, is that if it's Y equals just a number, it crosses only the Y axis at that number. If it's X equals a number, it crosses only the X axis. Nope, we're not finished, okay? The last type of problem are our application, our word problems.
Oh no.
So the takeaway that I want you to take from this is the fact that with a line, something has to be consistent, okay? In this particular case, it says swimming at the park pool costs $2.75 for each person. The total cost is given by this function where X is the number of people going swimming. Graph this function. Well, what was consistent? It was consistent the fact that every person costs $2.75. So what happens? The more people, what happens to the amount of money? Goes up, because the more people that go, the more money that they bring in or they charge. So every time the line goes up, but it stays straight.
The following have been in the